So we want to start using what are called matrices to organize our work, and we can use them in several applications in this course and in other courses. But first, let's just define what a matrix is and how those are set up. So a matrix is just a rectangular array of numbers. We can use them to do this elimination process in an easier and cleaner way, because basically what we get to do is we get to drop out the variables. We do not have to carry through the x, y's, and z's, and it just makes it a lot easier to look at and to work with and a little bit cleaner. So we have this system of three equations shown here with the x, y's, and z's in them. If we turn that into its matrix representation, this is what it looks like. So what you notice is that there are kind of a couple parts to it. There is this first part called the coefficient matrix. And what that's made up of are all of the coefficients on the left-hand side. There's a 1 here, so that's where that 1's coming from, and a 1 here as well. So we drop out the x, y's, and z's, and we only write out the coefficients. Then the constants are separated by a line that represents where the equal to sign landed in all of those equations. And then the constants are over on the right-hand side of that. The entire matrix that you're looking at here is called the augmented matrix. So if you ever are asked to make an augmented matrix, that's what they mean. They mean put your coefficients on the left, put your bar where the equal to sign would be, and your constants on the right-hand side. When you would work through and work on this, which we're going to learn how to do in just a minute, the final solution would look like this matrix, where the x, y's, and z's are not written, but they are understood to be in their respective places. And what you can end up doing is following over these ones to their answer. So this would be saying x is equal to 1, y is equal to 0, z is equal to 2, and we have the final solution, order triple 1, 0, 2. Now, we're going to learn how to get from this starting point to this finishing point momentarily. But let's go ahead and just talk about some of the features of these matrices. So what we like to get to is what's called row-reduced form. So this is when your augmented matrix with m rows and n columns, called an m by n matrix. It's in row-reduced form if it satisfies these conditions. If each row consisting entirely of zeros lies below any other row having non-zero entries. So if you do end up in the process of your work getting a whole row of zeros, it has to go on the bottom. That's rule number 1. That basically means it was a duplicate of another row and it was unnecessary, so we just put it on the bottom. Second rule is the first non-zero entry in each row is now a 1 called a leading 1. So as you come in from the left-hand side, the first thing you have to hit is a 1. And we'll look at these in a second. Third rule, if any two successive non-zero rows in any of them, the leading 1 has to be to the lower right of the leading 1 in the upper row. So the 1s basically have to make a diagonal like this. They have to go down and to the right. And then the last rule is that if a column contains a leading 1, then all the other entries in that column are zeros. So let's actually look at a few and apply those rules and see, are these in row-reduced form or not? And if it's not, we're going to state which one of these rules it violates. So let's see, if we're looking at A, first of all, there's no row, and rows are horizontal, right? So there's no row consisting entirely of zeros, so that is not an issue. The first non-zero entry in each row is a 1. So as I come in here, the first entry I hit there is a 1, so that check. Now it says the first non-zero entry. So as long as so that's 0. The first number that's not a 0 is a 1. Check. The first number that's not a 0 is a 1. Check. So we've hit 1 and 2. Okay, so if you have a leading 1, it has to be to the lower right of the one above it. So what we can see here is that's okay. Here's my leading 1. The next leading 1 has moved down to the right, and the next leading 1 is down to the right. So we're good on that one as well. They're moving down and to the right as you go. And if it has a leading 1 in any column, all the other entries in that column have to be 0. So now if we're looking in the columns, here's a leading 1. All of the other entries are zeros. Check. Here's a leading 1. All of the other entries are zeros. Check. Here's a leading 1. All the other entries are zeros. So this one is perfectly fine. This one, yes, is in what we would call row reduced form. It hits all those criteria. Now B, I'm going to be able to say no immediately because it fails number 1. It's got a row of all zeros that needs to be moved to the bottom. So that's an easy fix, but it's definitely not correct how it is. It's actually okay in the other rules because the first thing I hit that's not a 0 is a 1. If I have a 1, the other entries are zeros, and the ones are moving down to the right. So it hits everything else. So all we would need to do is a simple move those zeros down to the bottom. But as of right now, no, it's not. So I'm just going to write 0 row not on the bottom. So it violated number 1. Okay, let's look at C. I don't have any row of all zeros, so that one can't be an issue. The first non-zero entry in each row is a 1, so let's check that. The first thing I hit that's not a 0 is a 1. First thing I hit that's not a 0 is a 1. And this one happens to be all zeros because we're really only checking the left-hand side. So that one's okay. So we have our leading 1s here and here. The ones are moving down to the right. Agreed. This one is down and to the right of this one, so that's okay. And if it has a leading 1, the other entries are zeros. So here's a leading 1, everything else there is a 0. There's no leading 1 in the second column, so that doesn't matter. And here's another leading 1, and everything in its column is a 0. So this one's actually a yes. I know this 2 right here might be bothering you, but it's fine. That doesn't actually violate any of those rules. It's technically still in what we call row reduced form. Okay, let's try this last one. No all 0 row, so number 1 is fine. The first non-zero entry is a 1. Let's check that. So the first thing I hit here that's not a 0 is a 1. The first thing I hit here that's not a 0 is a 1. The first thing I hit here that's not a 0 is not a 1. It's a 2. So it's violating number 2. The first non-zero element is 2, not 1. So that's wrong. And it also happens to violate number 4 because of that. Because what we've got then here is we have a leading 1 in this row, and not everything else in that column is a 0. So it also violates number 4. So we've got a leading 1 with non-zero entries in that column. So that one would not be considered in row reduced form. Okay, so let's go ahead and just talk through a few definitions, and then we will cut this video here, and I'll see you in the next video. So a unit column is a column in a coefficient matrix if one of your entries is a 1 and the other entries are all zeros. So that's like that number 4. If you ever have a leading 1, you need the rest of the entries in that column to be zeros, and we call that then a unit column. So that's what we're going for on these. we're going to do a process called pivoting. That's when you transform a column of a matrix into a unit column. So I could fix this up here is what we're saying. I could fix a column that is not currently a unit column and turn it into one by performing some steps. Your pivot element is the element about which your matrix is pivoted, and I'm going to explain how do you choose a pivot element and how do you pivot in a later video. And we're going to use what are called row operations in order to do that. So those are the operations that we are allowed to perform on the rows of a matrix.